Arsenic contamination of groundwater is a form of groundwater pollution which is often due to naturally occurring high concentrations of arsenic in deeper levels of groundwater. It is a high-profile problem due to the use of deep tubewells for water supply in the Ganges Delta, causing serious arsenic poisoning to large numbers of people. A 2007 study found that over 137 million people in more than 70 countries are probably affected by arsenic poisoning of drinking water. Arsenic contamination of groundwater is found in many countries throughout the world, including the USA. Approximately 20 major incidents of groundwater arsenic contamination have been reported. Of these, 4 major incidents occurred in Asia, in Thailand, Taiwan, and mainland China. Speciation of arsenic compounds in water. Arsenic-contaminated water typically contains arsenic acid and arsenic acid or their derivatives. Their names as acids is a formality. These species are not aggressive acids but are merely the soluble forms of arsenic near neutral pH. These compounds are extracted from the underlying rocks that surround the aquifer. Arsenic acid tends to exist as the ions, has O4, 2A and H2 as O4, are in neutral water, whereas arsenic acid is not ionized. Contamination-specific nations and regions. India and Bangladesh. Arsenic contamination of the groundwater in Bangladesh is a serious problem. Prior to the 1970s, Bangladesh had one of the highest infant mortality rates in the world. Ineffective water purification and sewage systems as well as periodic monsoons and flooding exacerbated these problems. As a solution, UNICEF and the World Bank advocated the use of wells to tap into deeper groundwater. Millions of wells were constructed as a result. Because of this action, infant mortality and diarrheal illness were reduced by 50%. However, with over 8 million wells constructed, approximately 1 in 5 of these wells is now contaminated with arsenic above the government's drinking water standard. In the Ganges Delta, the affected wells are typically more than 20 meters and less than 100 meters deep. Groundwater closer to the surface typically has spent a shorter time in the ground, therefore likely absorbing a lower concentration of arsenic. Water deeper than 100 m is exposed to much older sediments which have already been depleted of arsenic. The issue came to international attention in 1995. The study conducted in Bangladesh involved the analysis of thousands of water samples as well as hair, nail, and urine samples. They found 900 villages with arsenic above the government limit. Criticism has been leveled at the aid agencies, who denied the problem during the 1990s while millions of tube wells were sunk. The aid agencies later hired foreign experts who recommended treatment plants that were inappropriate to the conditions, were regularly breaking down, or were not removing the arsenic. In West Bengal, India, water is mostly supplied from rivers. Groundwater comes from deep tubewells, which are few in number. Because of the low quantity of deep tubewells, the risk of arsenic poisoning in West Bengal is comparatively less. According to the World Health Organization, in Bangladesh, West Bengal, and some other areas most drinking water used to be collected from open dug wells and ponds with little or no arsenic, but with contaminated water transmitting diseases such as diarrhea, dysentery, typhoid, cholera, and hepatitis. Programs to provide safe drinking water over the past 30 years have helped to control these diseases, but in some areas they have had the unexpected side effect of exposing the population to another health problem, arsenic. The acceptable level as defined by WHO for maximum concentrations of arsenic in safe drinking water is 0.01 mg per litre. The Bangladesh government's standard is at a slightly higher rate, at 0.05 mg per litre being considered safe. WHO has defined the areas under threat. 7 of the 19 districts of West Bengal have been reported to have groundwater arsenic concentrations above 0.05 mg per litre. The total population in these 7 districts is over 34 million while the number using arsenic-rich water is more than 1 million. That number increases to 1.3 million when the concentration is above 0.01 mg per litre. According to a British Geological Survey study in 1998 on shallow tube wells in 61 of the 64 districts in Bangladesh, 46% of the samples were above 0.01 mg per litre and 27% were above 0.050 mg per litre. When combined with the estimated 1999 population, it was estimated that the number of people exposed to arsenic concentrations above 0.05 mg per litre is 28 to 35 million and the number of those exposed to more than 0.01 mg per litre is 46 to 57 million. Throughout Bangladesh, as tube wells get tested for concentrations of arsenic, ones which are found to have arsenic concentrations over the amount considered safe are painted red to warn residents that the water is not safe to drink. One solution is by using surface water and instituting effective withdrawal regulation. West Bengal and Bangladesh are flooded with surface water. We should first regulate proper watershed management. Treat and use available surface water, rainwater, and others. The way we're doing it at present is not advisable. Another avenue would be looking at the nutrition content, which is also seen to be responsible for mitigating the effects of arsenic. Malnutrition is seen to increase the adverse effects of arsenic. In Bihar, groundwater in 13 districts have been found to be contaminated with arsenic with quantities exceeding 0.05 mg per litre. All these districts are situated close to large rivers like Ganga and Gandak. Argentina the central portion of Argentina is affected by arsenic-contaminated groundwater. Specifically, the La Pampa produces water containing 4 to 5,300 micrograms per litre. United States Regulation, a drinking water standard of 0.05 mg per litre. Arsenic was originally established in the United States by the Public Health Service in 1942. The Environmental Protection Agency studied the pros and cons of lowering the arsenic maximum contaminant level for years in the late 1980s and 1990s. No action was taken until January 2001, when the Clinton administration in its final weeks promulgated a new standard of 0.01 mg per litre to take effect January 2006. The Bush administration suspended the midnight regulation, but after some months of study, the new EPA Administrator Christine Todd Whitman approved the new 10 ppb arsenic standard and its original effective date of January 2006. Many locations exceed this limit. Cases of groundwater-caused acute arsenic toxicity, such as those found in Bangladesh, are unknown in the United States, where the concern has focused on the role of arsenic as a carcinogen. The problem of high arsenic concentrations has been subject to greater scrutiny since 2001, when the federal government promulgated a new lower standard for arsenic in drinking water. Many public water supply systems across the United States obtain their water supply from groundwater that had met the old 50 ppb arsenic standard but exceeded the new 10 ppb MCL. These utilities searched for either an alternative supply or an inexpensive treatment method to remove the arsenic from their water. In Arizona, an estimated 35% of water supply wells were put out of compliance by the new regulation. In California, the percentage was 38%. The proper arsenic MCL continues to be debated. Some have argued that the 10 ppb federal standard is still too high, while others have argued that 10 ppb is needlessly strict. Individual states are able to establish lower arsenic limits. New Jersey has done so, setting a maximum of 0.005 mg per litre for arsenic in drinking water. A study of private water wells in the Appalachian Mountains found that 6% of the wells had arsenic above the US MCL of 0.010 mg per litre. Case studies and incidents. Fallon, Nevada has long been known to have groundwater with relatively high arsenic concentrations. Even some surface waters, such as the Ver in Arizona, sometimes exceed 0.01 mg per litre arsenic, especially during low flow periods when the river flow is dominated by groundwater discharge. A study conducted in a contiguous 6-county area of southeastern Michigan investigated the relationship between moderate arsenic levels and 23 selected disease outcomes. Disease outcomes included several types of cancer, diseases of the circulatory and respiratory system, diabetes mellitus, and kidney and liver diseases. Elevated mortality rates were observed for all diseases of the circulatory system. The researchers acknowledged a need to replicate their findings. Nepal Nepal is subject to a serious problem with arsenic contamination. The problem is most severe in the Tri region, the worst being near Nawalparsi district, where 26% of shallow wells failed to meet WHO standard of 10 ppb. A study by Japan International Cooperation Agency and the Environment in the Kathmandu Valley showed that 72% of deep wells failed to meet the WHO standard, and 12% failed to meet the Nepali standard of 50 ppb. Water purification solutions small-scale water treatment A review of methods to remove arsenic from groundwater in Pakistan summarizes the most technically viable inexpensive methods. A simpler and less expensive form of arsenic removal is known as the sono-arsenic filter, using 3 pitchers containing cast iron turnings and sand in the first pitcher and wood-activated carbon and sand in the second. Plastic buckets can also be used as filter containers. It is claimed that thousands of these systems are in use and can last for years while avoiding the toxic waste disposal problem inherent to conventional arsenic removal plants. Although novel, this filter has not been certified by any sanitary standards such as NSF, ANSI, WQA and does not avoid toxic waste disposal similar to any other iron removal process. In the United States, small under-the-sink units have been used to remove arsenic from drinking water. This option is called point-of-use treatment. The most common types of domestic treatment use the technologies of adsorption or reverse osmosis. Ion exchange and activated alumina have been considered but not commonly used. Chaff-based filters have been reported to reduce the arsenic content of water to 3 microgram per liter. This is especially important in areas where the potable water is provided by filtering the water extracted from the underground aquifer. Large-scale water treatment in some places, such as the United States, all the water supplied to residences by utilities must meet primary drinking water standards. Regulations may necessitate large-scale treatment systems to remove arsenic from the water supply. The effectiveness of any method depends on the chemical makeup of a particular water supply. The aqueous chemistry of arsenic is complex, and may affect the removal rate that can be achieved by a particular process. Some large utilities with multiple water supply wells could shut down those wells with high arsenic concentrations, and produce only from wells or surface water sources that meet the arsenic standard. Other utilities, however, especially small utilities with only a few wells, may have no available water supply that meets the arsenic standard. Coagulation filtration removes arsenic by coprecipitation and adsorption using iron coagulants. Coagulation filtration using alum is already used by some utilities to remove suspended solids and may be adjusted to remove arsenic. But the problem of this type of filtration system is that it gets clogged very easily, mostly within 2 to 3 months. The toxic arsenic sludge are disposed of by concrete stabilization, but there is no guarantee that they won't leach out in future. Iron oxide adsorption filters the water through a granular medium containing ferric oxide. Ferric oxide is a high affinity for adsorbing dissolved metals such as arsenic. The iron oxide medium eventually becomes saturated, and must be replaced. The sludge disposal is a problem here too. Activated alumina is an adsorbent that effectively removes arsenic. Activated alumina columns connected to shallow tube wells in India and Bangladesh have removed both As3 and As-B from groundwater for decades. Long-term column performance has been possible through the efforts of community-elected water committees that collect a local water tax for funding operations and maintenance. It has also been used to remove undesirably high concentrations of fluoride. Ion exchange has long been used as a water softening process, although usually on a single home basis. Traditional anion exchange resins are effective in removing As-B, but not As-3, or arsenic trioxide, which doesn't have a net charge. Effective long-term ion exchange removal of arsenic requires a trained operator to maintain the column. Both reverse osmosis and electrolysis can remove arsenic with a net ionic charge. Some utilities presently use one of these methods to reduce total dissolved solids and therefore improve taste. A problem with both methods is the production of high salinity wastewater, called brine, or concentrate, which then must be disposed of. Subterranean arsenic removal technology (SAR technology). In subterranean arsenic removal, aerated groundwater is recharged back into the aquifer to create an oxidation zone which can trap iron and arsenic on the soil particles through adsorption process. The oxidation zone created by aerated water boosts the activity of the arsenic oxidizing microorganisms which can oxidize arsenic from +3 to +5 state SAR technology. No chemicals are used and almost no sludge is produced during operational stage since iron and arsenic compounds are rendered inactive in the aquifer itself. Thus toxic waste disposal and the risk of its future mobilization is prevented. Also, it has very long operational life, similar to the long-lasting tube wells drawing water from the shallow aquifers. 6 such SAR plants, funded by the World Bank and constructed by Ramakrishna Vivekananda Mission, Barrackpore and Queen's University Belfast, UK are operating in West Bengal. Each plant has been delivering more than 3,000 litres of arsenic and iron-free water daily to the rural community. The first community water treatment plant based on SAR technology was set up at Kashimpur near Kolkata in 2004 by a team of European and Indian engineers led by Bhaskar Senator Gupta of Queen's University Belfast for Teapot. SAR technology had been awarded to Rubhai Ambani Award, 2010 from IHME UK for chemical innovation. Again, SAR was the winner of the St Andrews Award for Environment, 2010. The SAR project was selected by the Blacksmith Institute, New York and Green Cross Switzerland as one of the 12 cases of cleanup and success in the World's Worst Polluted Places Report 2009. Currently, large-scale SAR plants are being installed in USA, Malaysia, Cambodia, and Vietnam. Dietary intake. Researchers from Bangladesh and the United Kingdom have claimed that dietary intake of arsenic adds a significant amount to total intake where contaminated water is used for irrigation. See also, arsenic poisoning, Gringer challenge, toxic heavy metal. References. Further reading, Nixon R.T., MacArthur J.M., Ravenscroft P. Mechanism of arsenic release to groundwater, Bangladesh and West Bengal. Applied Geochemistry 15, 403 Euro 413 doi, 10.1016 per second 0883-2927, 99, 00086-4. Corte Northeast, Fernando Q. A Review of Arsenic, 3, in Groundwater. Critical Reviews in Environmental Control 21, 1 Euro 39 doi, 10.1080/10643389109388408. Smith A. H., Lingazio, Raman M. Contamination of Drinking Water by Arsenic in Bangladesh, a Public Health Emergency. Bulletin of the World Health Organization 78, 1093 Euro 1103. doi, 10.1590 per second 0042-9686200000900005. PMC 2,560,840. PMID 11,019,458. Harvey C.F., Swartz C.H., Badruzzaman A.B.M. Arsenic Mobility and Groundwater Extraction in Bangladesh. Science 298, 1602 Euro 1606. doi, 10.1126/Science 1,076,978. PMID 12,446,905. Raghavan T. Screening of rice cultivars for grain arsenic concentration and speciation. American Society of Agronomy Proceeding. Hussain M.F. Arsenic Contamination in Bangladesh, an Overview. Agriculture Ecosystem and Environment 113, 1 Euro 16 doi, 10.1016/JAG. 2005.08.034. External links, ATSDR, Case Studies in Environmental Medicine, Arsenic toxicity, arsenic in groundwater. IGRAC International Groundwater Resources Assessment Center, Arsenic in Groundwater, a World Problem, IAH publication, Netherlands National Chapter, 2008. Somali Shillings. Arsenic.net, information and awareness raising site, focused on Bangladesh. Contamination of drinking water by arsenic in Bangladesh, a public health emergency, at sos-arsenic.net. Subterranean arsenic treatment technology in West Bengal, 12 cases of cleanup and success, www.wbphed.gov.in, arsenic scenario of West Bengal, drinking death in groundwater, arsenic contamination as a threat to water security for Bangladesh, ACDIS occasional paper by Mustafa Moinuddin. St Andrews Prize for Environment 2010.